Now we'll discuss about edge chasing. A distributed approach to deadlock detection uses a technique called edge chasing or path pushing. In this approach, a global weight for a graph is not constructed, but each of the server involved has knowledge about some of its edges. The server attempts to find a cycle by forwarding a messages called probes which follow the edges of the graph throughout the distributed system. A probe message consists of a transaction wait for a relationships representing a path in a global wait for a graph. The question is, when should server send out a probe? Consider the situation at a server X in a figure. This server has just added a edge W to U to its local wait for a graph, and at this time transaction U is waiting to access object B which transaction V holds at a server Y. This edge could possibly a part of a cycle V to T1, T1 to T2, so on to W, on to U to V, involving a transaction using an object at other server. This indicates that there is a potential distributed deadlock cycle which could be found by sending out a probe to server Y. Now consider the situation a little earlier when a server Z adds an edge V to W to its local graph. At this point in a time, W is not waiting. So there is no point in sending out a probe. Each distributed transaction starts at a server called as coordinator of the transaction and moves to several other servers called participants in transaction which can communicate with coordinator. At any point in time, a transaction can either be active or waiting at just one of these servers. The coordinator is responsible for recording whether the transaction is active or is waiting for a particular object, and participant can get this information from their coordinators. A lock manager informs the coordinators when the transaction starts waiting for objects and when the transactions require objects and become active again. When a transaction is aborted to break a deadlock, its coordinator will inform the participants and all of its locks will be removed, with the effect that all the edges involving that transactions will be removed from local wait for graphs. Edge chasing algorithm has following steps. Step number 1, called as initiation. When a server notes that transaction T starts waiting for another transaction U, where U is waiting to access an object at another server, it initiates a detection by sending a probe containing a edge T to U to the server of the object at which the transaction U is blocked. If U is sharing a lock, probes are sent to all the holders of the lock. Sometimes further, transaction may start sharing the lock later on, in which case probes be sent to them too. Second step, called a detection step. Detection consists of receiving a probes and deciding whether a deadlock has occurred and whether to forward the probes. For example, when a server of an object receives a probe T to U indicating that T is waiting for a transaction U that holds a local object, it checks to see whether U is also waiting. If it is, transaction it waits for, say for example transaction V, is added to the probe, making it T to U, U to V, and if the new transaction V is waiting for another object elsewhere, the probe is forwarded. In this way, paths through the global wait for a graph are built one edge at a time. Before forwarding a probe, the server checks to see whether the transaction, for example T, it just added has caused a probe to contain a cycle, that is for example T to U, U to V and V to T. If this is the case, it has found a cycle in the graph and deadlock has been detected. The resolution is when a cycle is detected, the transaction in the cycle is aborted to break the deadlock. In our example, the following steps describe how deadlock detection is initiated and probes that are forwarded during the corresponding detection phase. Server X initiates a detection by sending a probe W to U to the server of B, that is to server Y. Then server Y receives a probe W to U, notes that B is held by transaction V and appends V to the probe to procedure to produce W to U, U to V. It notes that V is waiting for C at server Z. This probe is forwarded to server Z. Server Z receives a probe W to U, U to V, notes C is held by W and appends W to the probe to produce W to U, U to V and V to W. This path contains a cycle. The server detects a deadlock. One of the transactions in the cycle must be aborted to break the deadlock. The transaction to be aborted can be chosen according to transaction priorities, which we are going to see next. Figure shows the progress of a probe messages from initiation by server of A to the deadlock detection by server of C. In most of the edge chasing algorithms, the server of an object sends a probe to the transaction coordinators, which then forwards them to the server of the object for which the transaction is waiting. In our example, the server of a B transmits a probe W to U, U to V to the coordinator of a V, which then forwards it to the server of a C. This shows that when a probe is forwarded, two messages are required. The above algorithm should find any detection that occurs, provided that waiting transactions do not abort and there are no failures such as lost messages or servers crashing. To understand this, consider a deadlock cycle in which the last transaction W starts waiting and completes the cycle. When W starts waiting for an object, the server initiates a probe that goes to the server of the object held by each transaction for which W is waiting. The recipient extends and forwards the probes to the server of objects requested by all waiting transactions they find. Thus, every transaction that W waits for, directly or indirectly, will be added to the probe unless a deadlock is detected. When there is a deadlock, W is waiting for itself indirectly. Therefore, the probe will return to the object that W holds. We'll see now transaction priorities. In the above algorithm, every transaction involved in deadlock cycle can cause deadlock detection to be initiated. The effect of several transactions in a cycle initiating a deadlock detection is that detection may happen at several different servers in the cycle, with the result that more than one transaction in a cycle is aborted. Consider transactions T, U, V and W, where U is waiting for W and V is waiting for T. At about the same time, T requests an object held by U and W requests object held by V. Two separate probes T to U and W to V are initiated by servers of these objects and are circulated until the deadlocks are detected by each of the servers. In figure B, the cycle is T to U, U to V, V to T, and in figure C, the cycle is W to V, V to T, T to U, and U to W. In order to ensure that only one transaction in a cycle is aborted, the transactions are given a priorities in such a way that all transactions are totally ordered. Timestamps, for example, may be used as a priorities. When a deadlock cycle is found, the transaction with a lowest priority is aborted. Even if several different servers detect a same cycle, they will all reach the same decision as to which transaction is to be aborted. We write T greater than U to indicate that T has higher priority than U. In the above example, assume T is greater than U, which is greater than V, which in turn greater than W. Then the transaction W will be aborted when either of the cycles, that is T to U, U to W, W to V, and V to T, or cycle W to V, V to T, T to U to W is detected. It might appear that transaction priorities could also be used to reduce the number of situations that cause deadlock detection to be initiated by using a rule that detection is initiated only when higher priority transaction starts wait for a lower priority one. In our example, as T is greater than U, the initiating probe T to U would be sent, but as W is less than V, the initiating probe W to V would not be sent. If we assume that when a transaction starts waiting for another transaction, it is equally likely that waiting transaction has higher or a lower priority than the waiting for transaction, then the use of this rule is likely to reduce the number of probe messages by about half. Transaction priorities could also be used to reduce the number of probes that are forwarded. The general idea is that probes should travel downhill, that is, from transaction with higher priorities to transaction with lower priorities. To this end, servers use the rule that they don't forward any probe to a holder that has higher priority than initiator. The argument for doing this is that if the holder is waiting for another transaction, it must have initiated a detection by sending a probe when it has started waiting. However, there is a pitfall associated with these apparent improvements. In our example, in a figure, transactions U, V, and W are executed in order in which U is waiting for V and V is waiting for W when V starts waiting for U. Without the priority rules, detection is initiated when W starts waiting by sending a probe W to U. Under priority rules, this probe will not be sent because W is less than U and deadlock will not be detected. The problem is that the order in which the transaction starts waiting can determine whether or not deadlock will be detected. The above pitfall can be avoided by using a scheme in which the coordinator saves a copy of all the probes received on behalf of each transaction in a probe queue. When a transaction starts waiting for an object, it forwards the probe in its queues to the server of the object, which propagates the probes on downhill routes. In the figure you can see when U starts waiting for V, the coordinator of a V will save the probe U to V as shown in the figure A. Then V starts waiting for W, the coordinator of W will store V to W and V will forward its probe Q U to V to W. Now as per the figure B, in which W's probe Q has U to V and V to W. When W starts waiting for A, it will forward its probe Q U to V, V to W to the server of A, which notes the new dependency W to U and combines it with the information in the probe received to determine that U to V and V to W and W to U, and then the deadlock is detected.